Hello, everyone. Today I'm going to give a talk about peeking into your app without actually seeing it, US state inference, and novel Android attacks. I'm Alfred Chen from University of Michigan in the RobustNet research group. So, it is well recognized that GUI security, more specifically the GUI content integrity and confidentiality, are very critical in achieving the end-to-end security. There are some previous work shows that an attacker can spoof your UI in the desktop or the browser environment by, for example, exploiting the GUI logic flaws, which breaks the GUI integrity. And also, a recent work shows that an Android malware can take screenshots without any privilege by exploiting the Android ADB vulnerability, and this breaks the GUI confidentiality. But today, I'm going to talk something else. It is about another form of GUI confidentiality breach, which is a weaker form, which has not been explored much. It is the US state an application is in, without knowing the exact pixels of the screen. So what does this mean? This means that we can see the state machine transitions, we can track your US state, but we cannot see the content inside your US state. So this means that we cannot directly steal your password username in the login US state. But even though we cannot do that, for lots of attacks, and for example on Android, this US state information is very useful because it can help them to enhance their efficiency by only attack those states of interest. For example, let's say a keylogger, he may only want to attack the login US state because this is where the password is entered compared to other states. So in our work, we want to study this, but we find that the security implication of the US state information is much more serious than we originally thought. For example, we have designed and implemented an attack which uses the US state information to find the best attack timing to carry out a seamless hijacking attack on the US state of the login and steal the username and password. This is an attack we named US state hijacking attack. And the goal is to hijack the sensitive US state to steal the private input, for example, your password. The attack works like this. So foreground is the victim map, for example, the Chase banking app. In the background is the attacker, for example, Android malware. The user interacts with the app and triggers the US state transitions. And the attacker is not just passively in the background listening, track the US states, and wait for the time. The time is when the login US state shows up. So he also prepared a fake login US state beforehand, just for the hijacking attack. So now the user going to login, and the attacker knows that because we can track the US state. So the attacker now quickly inject this fake US state into foreground and to do the hijacking. This hijacking is possible from background to foreground is because we exploit the UI preemption functionality in Android, which is the design functionality for apps like alarm or reminder app. And also, this injection is totally seamless because first, there's no screen glitches, so disable the animation. It is allowed in Android. And also second, we use US state to capture the best attack timing precisely. So the user just enter the username and password, then the attack succeeds. We have a video demo about this attack here on the text app HNR block. Yeah, should be this. So the phone on the left is just for displaying the attack progress, and the phone on the right is where the attack actually happens. There's the Android malware running in the background tracks the US state of the foreground app, the HNR block. The user keeps interacting with the app, and as we can see on the left, we can track the US state in real time. Okay, the user keeps interact, but these states are not very interesting, map, but now he's going to log in. We slow down this process because this is where the injection happens. As you can see, there's no screen glitches, and the process is totally transparent to the user. So note that we did some optimization to find the best attack timing in this attack. And from now on, the foreground US state belongs to the attacker. And we can see username and password just stolen. So it seems that we just use US state tracking breaks the GUI integrity. So can we also break the confidentiality? The answer is yes. We have some other attacks built on US state tracking. One of them is called camera peeking attack. The goal of this attack is to steal the sensitive pictures taken in Android apps. So nowadays, your app helps you use camera to do many things. For example, you can take a picture in your Chase banking app and deposit the money into your account without going to the local branch. These pictures usually contains tons of sensitive information, like on the check you got your home address, your bank account number, routing number, even your signature. So the designers usually keep these pictures well protected and are never returned to the external storage and make it publicly accessible. But with US state tracking, we can steal them very successfully and break the GUI confidentiality. We have a demo for that too. So as the previous video, the left phone is for displaying the attack progress, and left phone is where the attack happens. So the user is not going to take picture of the check and deposit the money. So you can see, he take picture, and at this time, the attacker get a message. So, okay, check image received. And let's check out this image. As we can see, this image is exactly the one the user just taken. And if we zoom in for a little bit, and we can see all the sensitive information being stolen here. And also, besides these two attacks, it can also, the US state tracking can also be used to monitor and analyze the user behavior, which also breaks the GUI confidentiality. And it can also be used to enhance the existing attacks in both stealthiness and effectiveness. So what are the lessons here? So seems that US state leakage can be very dangerous because it can lead to both GUI integrity and confidentiality breaches. So, and we found that actually the situation is much worse because US state information is not protected well. And an unprivileged application can track another app's US state in real time. And this is an attack named US state inference attack. We define US state as a mostly consistent UI at window level for certain program functionality, for example, login. So on Android, this is also called an activity, which is a full screen window. So on Android, this attack is also called activity inference attack. In this attack, an unprivileged app can infer the foreground activity of another app in real time. And this process requires no Android permission. The underlying causes for this attack is that in the Android GUI framework design, every US state changes can be unexpectedly observed through a publicly accessible side channel, which is a newly discovered shared memory side channel, and we found can affect nearly all popular operating systems. The general steps of the attack is like this. First, we detect the activity transition. This is just a single bit of information about whether the transition happens or not. After this, we infer the activity when the new activity just shows up. So at this step, we know which activity it is. The newly discovered shared memory side channel is the major enabler for the first step, and with some other side channels, we can infer the activity in the second step. After this, we can launch the follow-up attacks, which we just demonstrated before. Let's first introduce the shared memory side channel. We find that the shared virtual memory size changes are correlated with the Android window events. Let's say this is the Android app, and at the same time, we monitor the shared virtual memory size in a public file in proc file system. When there is a window pop-up, you will see an increase, and when there is a window close, you will see a decrease there. And the increase and decrease size are proportional to the window size. This gives attacker a very good chance that if he can see this increase and decrease, then he can conclude a window pop-up or the close events. Since activity is a full screen window, this helps us to detect the activity transition, right? So the root cause for this correlation lies in the Android window manager design. So in Android, the app will first draw their activity window content to an off-screen buffer, then use a certain type of IPC to communicate this buffer to window compositor, which is the system process. The window compositor will composite all the off-screen buffers from all the applications into one image, then draw to the screen. After reading the source code, the change size in the memory is the off-screen buffer size, and the root cause is here in the IPC. For better UI join performance, Android used shared memory as this IPC. So this is why we can see the shared memory size changes in both the app side and the window compositor process. We have confirmed that shared memory is used in GUI design for many popular operating systems, like Android, iOS, macOS, Windows, and also VLAN for Linux. So after knowing this, detect the activity transition is simply a matter of detect a pattern in the shared memory size change. We got some nice property here which can have very high accuracy. First, most of the computation or the operation in Android app is done in the private memory space. So the shared memory space is fairly clean. And also, we got some unique patterns in the shared memory size changes. First is that the amount of the change size is fixed. It's a full screen window size, which is, as we said, activity is a full screen window. And the increase and decrease will both happen in this transition, because for the increase, it is the buffer allocation for the new activity, and for the decrease, it is the deallocation for the buffer for the previous activity. Both of these things are not very likely to happen randomly in practice. So after we detect an activity transition, the next step is to infer the activity. So here we design to use a signature for each activity, and also we build an activity transition graph to help it. The training phase is offline. We use a tool to automatically trigger the activity transitions. And in this process, we collect the transition feature data, which is used to create an activity signature. We also build the activity transition graph, which is used to build the transition model. In the attacking phase, which is online, now the user triggers the activity transition. The attacker just collects the feature data in the background and use the signature and transition model to infer the activity. For the signature design, we use various features collected during the transition process. And in our design, we have 4 features. The content provider activity, which is the database for Android, and network activity input method CPU utilization time feature. So all of this can be obtained freely in your system. For the remaining steps, we create an activity transition model using hidden Markov model. And also, the inference results are generated in the form of a list of activities in decreasing order of their probabilities. So now it's time to evaluate our method. We implement it in the C++, compile with Android NDK. We collect the data using our automated activity transition tool, which is the tool to generate the activity transitions on Samsung Galaxy S3 device with Android 4.2. We do the experiments on 7 popular Android apps, like popular health apps, banking apps, financial apps, shopping apps, something like that. So here are the results. For the transition detection, the accuracy is more than 96.5%, and the false positive and false negative rates are both under 4%. This is mainly because the channel is very clean, and also we got some unique patterns we just discussed before. And also, for the inference, the accuracy can achieve 80 to 90% for 6 out of 7 popular apps. This is mainly because the CPU and network works pretty well, and the transition model also helps a lot. The inference computation time is less than 10 milliseconds, and the inference delay, the time from the activity transition to the inference result being generated, is less than 1.3 seconds. We also improved them to 500 milliseconds for faster and more seamless activity hijacking, as you'll see in the video at the beginning. For the overhead, with our attack running in the background, the power usage increased by 2 to 6%. So we just see the US state can be inferred without any privilege. And also, the follow-up attacks breaks both the GUI confidentiality and integrity. So any idea how to defend against it? The first direction is to eliminate this side channel. So one idea is to enhance the access control in the profile system. And we found that Android already limits the access to some of the files which are previously publicly accessible in Linux. For example, those stack and instruction pointers, which are found to be used to infer the keystrokes. But our attack shows that there's still a long way to go in this direction. And also, another idea is to reuse the window buffers. In our activity transition pattern, we saw the buffer allocation and deallocation both in the transition process. So why not just pre-allocate double the buffers and reuse them in all the transitions? So then the pattern just disappears. The downside is that this may consume more memory since each buffer is several megabytes in size. But we think this is feasible in the future because smartphones now getting increasingly larger memory size, right? And also another direction for defense is to mitigate those follow-up attacks. For example, those USD hedging attack. One idea is to build a trusted path between the user and app so that we can defend against those phishing attacks. But these ideas, for these ideas, we think more efforts is definitely needed for us to investigate their effectiveness, because most of them do require significant changes in the system, which may affect the backward compatibility and the functionality. To summarize, we demonstrate a serious security implications for a new form of grid confidentiality breach. We formulated a general USD inference attack, which can infer USD in real time, which is enabled by a newly discovered shared memory side channel, which potentially affects all popular grid systems. We design and implement it on Android and further build several new attacks like the USD hedging attack. For more attack video demos, please visit our website, tinyurl.com, USD Inference. So, questions? Thank you.
Questions?
Dan Wallach, Rice University. I was wondering if you could tell me a little bit more about your thoughts on trusted path. How can an app be hacked to, or how can Android be hacked to prevent somebody from popping on top of you?
So, for example, if you build something in the system, you actually can ensure that so none of the other apps or the non-root process can preempt your UI. So you can displace something can never be preempt. Actually, if you do it in the system, for example, you can set this the Z index to be on the top, right? So if we have this, then this is a trust path which can authenticate the user and the app.
The other question is, have you spoken to anybody at Google about this? How are they responding?
Yeah, actually we are now working on that because currently we don't have a very good plan to solve this problem. So we are still testing the effectiveness of some defense ideas about this attack. So once we got some ideas, we definitely want to contact Google.
Well, like NC State, I think I may have missed the details of this, and it might have been in the talk, but how device-specific are the attacks? Do things like changes in screen size change the features that you're searching for?
Are you talking about the hedging attack or something?
Yeah, so you're looking when the specific activity was being shown to identify that within the buffer, right? Were the features you were looking for, would those change if you went to a device that had a different size screen?
Oh yeah. So yeah, this is a very very good question. So one thing, if you think about it, so the most of the popular device of like are just those several of them, right? So you can just design attack for several of them beforehand if you want to configure them pretty well beforehand. Another thing is that you can actually test the shared memory changes of yourself, and you can get an idea about how the environment of the new device you are now on. So after this, you can just change those features in your database, and then you can infer. You can just get a better inference results.
So takes a little bit more homework to scale out wide. It takes more homework on the attacker's part to scale out to more devices.
Yeah, definitely. Thanks.
Time for one more.
So, Tiffany from CMU. So, I like your talk. It's very interesting to
Thanks.
know story GUI attacks. So, I'm out of curiosity. I noticed that currently your attack is based on Android 4.2. So I was wondering if you have already tested it on some later version of Android, and is the memory sharing mechanism has been changed during the later version, or what about some other operating systems?
I don't really think so. We can check that. But this is actually a trade-off between your UI join performance and this attack. Actually, if you want your UI delivering to be faster, then you need to use to use this shared memory, right? So that's why all the popular operating systems use shared memory. So if you want more secure, so you can block that, but your UI maybe just get slower.
Thank you.
Yeah.
Thank you, speaker.